So in this tutorial, we are going to solve some questions under sound wave. So I've got a number of questions with me here. So the first question is, a stone is dropped from rest into a well. The sound of the splash is heard exactly 2 seconds later. Find the depth of the well if the air temperature is 10 degrees Celsius. Okay, so let's first try to understand the question. So if we have a well, I'll just have a well here, okay, and then the height of this well, I'll call it h. It's the one we are trying to find, which we don't know. And then they are saying that a stone is dropped. So if this is the stone, there is water here, okay. So now the time it takes for this stone to reach here, okay, that is what we are going to call T1. I would note that one as T1. Then again, there is a time which it takes for this sound to travel from this level all the way to the top where the person is. So this total time, which is 2 seconds, it was the time, the addition of the time it took from this for this stone to reach down here, and at the same time the time it takes for the sound to travel from this point all the way to the top part. So meaning we've got two times, we've got T1 and T2. So T1 is the time it takes for the stone to reach on the bottom of the well. That is T1. So if I add T1 plus T2, T2 is the time it takes for it to move from the bottom here all the way to down. That is the sound now. So when I add T1 plus T2, I'm supposed to get 2 seconds. And I do know that I want to find the h. So I started from rest, meaning the initial velocity is 0. So d is equal to v initial times t plus half gt squared. Since the initial velocity is 0, this is going to be cancelled out. So I'll have this d is the same as h. So I'll say h will be equal to half gt squared. Now in this case, which t are we talking about? We're talking about T1. Okay, so I'll say half gt1 squared. Now since I don't have h, I also don't have T1, I'll call this equation 1. Again, the speed of sound in this case, the velocity of the speed of sound, we do know that the velocity is given by distance over time. Now in this case, this distance is the h, and my goal is to make this h as a subject of formula. So I'll say d will be equal to v. This is now the speed of sound in air. So the speed of sound in air is going to be now T2. The time it takes for the sound to travel from this part here all the way to go up, that is T2. So I'll say times T2, like that. Okay, so d is the same as h. So I would say like that. Okay, now I have got two formulas which I have to put them here. So I'll say my h will be equal to half gt1 squared. Another one is that h should be equal to v times t2. Now we can make t1 as a subject of formula, or even just t2 to make things simple. Let's make t2 as a subject of formula in this formula. So at this point I will discover to say the velocity, the h, this h and this h, they will be the same. Okay, so I need first to find t. So let's make t2 as a subject of formula. T2 will be equal to 2 minus t1, meaning that where there is t2 in this formula, initially these two h, we are supposed to equate them equal to each other. What do I mean? I'll say half gt1 squared will be equal to v times t2. So where there is t2, let's replace it with 2 minus t1. Okay, so I'll say half gt1 squared is equal to v open brackets, where there is t2 we put 2 minus t1. Now that we have got t1 both sides, the left side and the right side. But again, we have been told that find the depth of the well if the air temperature is 10 degrees. So I need to find the velocity when the air temperature was 10 degrees. and I know that V is equal to 331 times the square root of the temperature divided by 273. So this temperature we have to change it to Kelvin. So I'll say 273 plus the degrees, which is 10. That will be now the temperature in Kelvin. So I'll say 273 plus 10, which is 283. So my V will be equal to 331, the square root of 283 divided by 273, like that. So 283 divided by 273, the answer I get is 1.0366. I get the square root is 1.018 times 331. I'm getting 337. So the velocity now which we are talking about right now is 337 meters per second. Okay? Now that I have my velocity, I can plug in the values to find first the time. Now when I find the time, I need to come back and use this. Why am I going to use this? I cannot use this because this stone was falling under the influence of gravity. So gravity has to be included. That's why I'm going to use the first one. Okay? So I've equated this distance equal to each other. And then I'm going to say half GT1 squared is equal to, my V is 337, open brackets, 2 minus the T1 I don't know. So I can now plug in half. Since it was going down, the G will be positive because it was going under it was going toward the gravity, so it will be 9.8. Then T1 squared is equal to, if I multiply these two, I'll say 337 times 2, which is 674. Then minus 337 times T1 is 337 T1. So now I can get rid of this. Then I'll say half times 9.8 is 4.9. T1 squared is equal to 674 minus 337 T1. I can clearly see that I've got T1 and just T, meaning that is a quadratic equation. What's the best thing to do? I'm going to shift these to go to the left hand side. Okay, so I'll have 4.9 T1 squared plus 337 T1 minus, because this one when it goes this other side is going to be minus 674 is equal to 0. Now that I've got this equation here, I can use quadratic equation to find the value of T. I no longer need this. Okay. Then I also no longer need this. Let me just push this part here to be on top here. So using quadratic equation is going to be T is equal to negative B plus or minus the square root of B squared minus 4AC divided by 2A. So this is my M, this is my B, and this is my C. So T will be equal to negative 337 plus or minus the square root of 337 squared minus 4, the value of A is 4.9, then C is negative 674, like that. I divide this by 2, A is 4.9, like that. So I have T to be equal to negative 337 plus or minus, what is in the square root there? If I do 337 squared, negative and negative, this negative here and that negative will be plus. So I'm going just to say plus, then I'll say open brackets, 4 times 4.9 again times 674, then I close the brackets. So I'm getting 126,774.4. So now I get the square root of this. I'm getting 356.4. 0.06, which is the same as just 0.1. Then I divide this by 2 times 4.9 is 9.8. Now I'll create space here on top. So I'll have t will be equal to negative 337 plus 356.1, divide this by 9.8, or another value for t will be negative 337 minus 356.1 divided by 9.8. Okay, so what would be the value for t? I'll just do it direct. So it will be negative 337 plus 356.1. I'm getting 19.1. 19.1 divided by 9.8. So I'm getting T1 will be equal to, now this is T1 which we're finding, 1.94. Okay, 1.94. 1.94, 1.94, or I can just round it off and say 1.95 seconds. This one will give me negative, but time cannot be negative, so I'll just leave it that side. It's going to be negative 337 minus 356.1 divided by 9.8. So I'm getting negative 70.72 seconds. So the time, which is T1, is now 1.95. Now, since I have the formula which I can use to find the height, now that I have my T1, I said we are going to use the one which is having g because it was in a free fall motion, so it was falling under the influence of gravity. So it will be half gt1 squared. So half 9.8, then t is 1.95. Now I square it like that. So my height of the well is going to be 0.5 is 1 over 2 times 9.8 times 1.95. 1.95 I square it. So I'm getting my answer to be 18.6. Let me redo it. I'm saying we have 1.95 I square it times 9.8 times 1 over 2 is 0.5. So I'm getting 18.63 meters. So this is the height of the building. So now so this is the answer for this question. So you have first to, for these 2 seconds, it was the total time t1 plus t2. That is the key point which you have to take note there. Okay, then you have to find t1 because we have to use this formula where there is g, because the stone was falling under the influence of gravity. So that is it for the first question. Now I have got question 2, which is also very interesting, which is under spherical waves. Okay, yeah. So the question is, a person standing 1 meter from a portable speaker hears its sound at an intensity of 7.5 times 10 to the power negative 3 watts per square meter. Find the corresponding decibel level. Find the sound intensity at a distance of 35 meters, assuming that the sound propagates as a spherical wave. So what do we mean when we say spherical wave? In fact, let me just give you the basic idea behind spherical wave. So if you have got a spherical, okay, so now if you are standing here, this is a person, or maybe the source or the sound is coming from here. So from this point here all the way to that point, let's call it R1, that is the radius of the spherical. Then from that point all the way to the last point we'll have R2, but it will keep on going just like that and the wave will just be propagating. It will go. Now that is what we call the spherical wave. Now one thing we have to know is that whenever we are talking about intensity, intensity is given by the power divided by the area. Okay, because we are saying that intensity, the SI unit for intensity is watts per cube per square meter. Now this intensity, we have power divided by, so the area of the spherical wave is given by 4 pi r squared, like that, meaning that I can also replace the area with 4 pi r squared. So that's the basic idea behind intensity. So what we need to know is that intensity is given by power divided by area. But again, there is a formula which we have to be familiar with, the one for corresponding decibels. So the decibel is given by 10 log the intensity divided by intensity initial. Now this intensity initial is the hearing threshold, and this is constant. Okay, the I0 is always 1.00 times 10 to the power negative 12 watts per square meter. That is the hearing threshold. Okay, so you can only hear a sound which has got intensity of 1.0 times 10 to the power 12. So that's the basic idea behind spherical wave. Now, so if we have got two things, we have got if this is my spherical wave propagating in that manner, like I said, we are going to have from this point, this is the source. So from that point to there I'll call it R1. Then from that point to that I'll call it R2. So there is a ratio which we have to be familiar with. Okay, so let me call, I'm going to call this as intensity 1. Okay, I can even start with intensity 2. It's okay. Okay, let's start with intensity 1. So what we need to understand is that intensity 1 or intensity 2 divided by intensity 3 or intensity 1 should be equal to, and then even on top here I'll put power 1 divided by area 1. Okay, we're talking about 2 now, so I'll put 2 here. Even here I'll divide it by power 2 divided by area 2, but this power will not change. So initially I'll just say intensity 2 divided by intensity 1 is equal to, the power is the same. Okay, then I divide this by area 2 divided by power divided by area 1, like that. So this is the same as if I can put power divided by area 2, then I put divided by power divided by area 1. At the same time, it is power divided by area 2 times area 1 divided by power. So the power and power can go, so I'll only remain with area 1 divided by area 2. So what I'll have now is this ratio. I'm going to have intensity 2 divided by intensity 1 will be equal to area 1 on top divided by area 2, because of this one is down, or this one is down here, this one is on top. So what is area? So under spherical wave, area is given by 4 pi, area is given by 4 pi r squared. So I'll have to specify this. I'm going to say my area 1 will be 4 pi r1 squared divided by area 2 will be 4 pi r2 squared. Now I can clearly see that these two can cancel out. So I'll have area 2 divided by area 1 to be equal to area 1 squared divided by area 2 squared. This formula is very important, this ratio. In some books you will see this formula to be written as area 1 divided by area 2, or intensity 1 divided by intensity 2 is equal to area 1, okay, area 2 or radius 2 squared divided by the radius 1 squared, like this. So this and that, they are the same, so you choose which one to use. Now we'll be using this relationship for this question, and also the formula for the corresponding decibels for us to work out the first question. So the first question is saying find the corresponding decibels. Now, like I said, the formula which you need to know for decibel is 10 log open brackets the intensity divided by intensity initial. So intensity initial is always 1.0 times 10 to the power negative 12 watts per square meter. So this is the threshold hearing. Now I can plug in the values. This intensity which is on top here I have, which is 7.5. So this will be given by 10 log, then this one is 7.50 times 10 to the power negative 3. I divide this by 1.0 times 10 to the power negative 12, like that. So if I get my calculator, I'll say 10 log, click on log, then open the brackets, 7.50 exponent negative 3 divided by 1.00 exponent negative 12. Then I close the brackets. So the answer I'm getting is 98.75. So the SI unit for corresponding decibels is small b d then capital B. So this is the answer for the first part. Now the second question is saying find the sound intensity at a distance of 35 meters assuming that the sound propagates as a spherical wave. So if the sound propagates as spherical wave, we always use this ratio. So I'll have r1 squared divided by r2 squared, like that. Now the r is the distance in this case. So the first distance, which is r1, is this one. The second one is that one. So we want to find I2. Okay. So now if I plug in the values here, I2 I don't know. I1 is 7.0 times 10 to the power negative 3. Then R1 is 1.0. Now I square it. R2, this is supposed to be R2. So R2 is 35. Now I square it. Okay, so we cross multiply. We'll find that we'll have 35 squared is 1222. So 1225, not 22, times I2 will be equal to 7.50 times 10 to the power negative 3, like that. Now we can divide both sides. We divide both sides by 12.5. Even here 12.5. So my I2 will be equal to, so 7.50 exponent negative 3 or times 10 to the power negative 3 divided by 12.5. Okay, so 7.50 times 10 to the power negative 3 divided by 1225. So I'll put my answer in scientific notation. So that should be 6.12 times 10 raised to the power negative 6. Since I don't have space this side, allow me to put this answer here. So the intensity 2 will be equal to 6.12 times 10 to the power negative 6 watts per square meter, like that. So that's my answer for the first part. Then the third question, which is part C, is saying find the decibel at this point. Now they want us to use the same formula. 10 log I divided by I0. I0 is always constant. It's 1.0 times 10 to the power 12. Now this, the top part, I'll use this intensity because at the distance of 35, the intensity is this. So I'll have 10 log open brackets. The I is 6.12 times 10 raised to the power 6. The I initial is always this. Now what is our corresponding decibels? So 10 log open brackets 6.12 times 10 to the power negative 6 divided by 1.00 times 10 to the power negative 12. Then I close the brackets. So the answer I'm getting is 7 point. Oh, okay. What answer am I getting now? Okay, let me do it. I'm saying 10 log, open brackets, 6.12 times 10 to the power negative 6 divided by 1.0 times 10 to the power negative 12. 1.0 times 10 raised to the power 12. Then I close the brackets. Okay. So what answer am I getting? I'm getting 67.86 decibels. So 67.867, which is the same as 8 of 87 if I round it off, decibels. So this is my answer for the second part. Now this is making sense. When we had the intensity of this, the corresponding decibel was 98. Okay, now this has reduced to 6.12 times 10 to the power negative 6. We expect the corresponding decibel to reduce as well. That's why it is 66. 66 is less than 98, which is making sense. So initially, the basic idea which I've given you here is you can solve any question for spherical wave. Just know that ratio is very important. Know that the spherical wave is given by power divided by area. Then area of the spherical wave is given by 4 pi r squared. Okay, then the ratio again, that I2 divided by I1 is given by r1 squared r2 squared, like that. Then you can reshuffle them. That is just okay. Okay, so that is it for this question, which involves spherical wave and corresponding decibels. Okay, so now we are on question 3. So this question is very interesting. This question is coming from Doppler effect. Okay, so the question is saying two trains on separate track move toward each other. Okay, train 1 has a speed of 1.3 times 10 to the power 2 kilometers per hour. Train 2 has a speed of 90 kilometers per hour. Okay, then train 2 blows its horn, emitting a frequency of 5.00 times 10 to the power 2 hertz. What is the frequency heard by the engineer on train 1? So whenever we're talking about Doppler effect, what you need to know is we're going to have two things. We're going to have what we call the observer and the source. So anything which is emitting frequency, that is the source. In this case, train 2, it is the one which was blowing the horn, emitting the frequency of 5.00 times 10 to the power 2. That is the source. Okay, so you need just to know one thing. If you know that this is the source, the other one is going to be the observer. So I'm going to put train 1 here. That's train 1. I'll have train 2 here. I'll have train 2 here. So I have two trains. So they are saying that these two guys are moving toward each other. This is moving in that direction, moving in that direction. So this is train 1. That's train 2. So since we, from the question, they are saying that train 2 blows its horn, the one which is blowing its horn, or the one which is emitting frequency, is the one we call it the source. So train 2 in this case is the source. The remaining part is the observer. Once you know these two, and as long as you identify that this is the source, this is the observer, then it's going to be easy for you. So that's the basic idea behind Doppler effect. If you know that this is the source, the observer, then that's cool. Now another thing you see, you have to check, is the observer moving toward the source? Okay, I'll talk about that later. But now, one thing we need to know is that we have been given the speed. Okay, that train 1 was moving with a speed of 1.3 times 10 to the power 2 kilometers per hour. This other one was moving with 90 kilometers per hour. Now the best thing here is to convert this speed from kilometers per hour to meters per second. Okay, so what I'm going to do now is I'm going to start with the one for 1.3 times 10 to the power 10. So I'll say 1.30, which is kilometers, divided by in 1 hour times in 1 kilometer we have got 1 hour. So again I have to convert the hour. In 1 kilometers we have got 1000 meters. So again I'm going to say in 1 hour we have got 3600 seconds. So kilometers and kilometers will cancel, hour and hour will cancel. So I'm going to have 1.3 times 10 to the power 2, which is supposed to be times 10 to the power 2 times 10 to the power 2 times 1000. I divide this by 3600, so I'm getting 36, meaning that this velocity now is 36.11 meters per second. Let's convert 90. Okay, so I'll say 90 kilometers in 1 hour, then I'll have a 1000 meters in how many? In 1 kilometers I've got 1000. Then again I have to convert hours to seconds. In 1 hour we have got 3600 seconds. So kilometers and kilometers will go, hour and hour will go. So I'm going to have 90 times 1000, divide this one by 3600. I'm getting a 25 meters per second. That is now my speed in meters per second. Now the formula which we need to know under Doppler effect is this. This is the general formula. So if the frequency of the observer is given by the frequency of the source, then v plus or minus the velocity of the observer divided by v minus plus the velocity of the source. Now if you want to know more about this formula, the time we were talking about Doppler effect, I derived this formula. So you can just check out our video under Doppler effect if you are interested to know where this formula is coming from. So now in this case, this is the general formula which you have to know. Now our goal is to find the what? The frequency. So what I'm going to do now, I'm going to get rid of this to create space. Okay, I can also get rid of this since I have got this velocity now in meters per second. I can even put it there. Okay, so this is the general formula which you have to know. I'll put it here. Let me first get rid of this. So this is my general formula which I'm going to put it here. Now allow me to explain on how you can use this formula. So one thing you need to know is that there are two signs here. We have got plus or minus, then there is minus or plus down here. So once you come across the question, any question under Doppler effect, if you discover that the source and the observer, they are moving toward each other. Okay, if the source and the observer, they are moving toward each other, like in this case the source and the observer, they are moving toward each other, you use the VO as positive, then VS as negative, meaning that you are going to get the top part, you are going to use plus, the down part you use minus. in short, if you are able to identify the top part, if it's going to be minus on top here, definitely down here is going to be plus. If it's going to be plus on top here, definitely down here is going to be minus. Okay, so what we normally do is the top part will go with the top part, the bottom part will also go with the bottom part. But let me explain the situations now. So if the observer and the source, they are moving toward each other, on top you use positive. So the VO, the velocity of the observer, will be positive and the velocity of the source will be negative 1. Then now, if these two, if the source and the observer, they are moving away from each other, then the opposite is true. VO will be negative, VS will be positive. That is what you need to know. So these are two scenarios. Now there are also some other ones which you need to know, which is if the observer, if you discover that the observer moves toward the source, if the observer moves toward the source, then the source is stationary, it's not moving, it is at rest. Okay, meaning that the VO will be positive. So once you know that the VO is positive, down is going to be negative, meaning that VS will be negative. That is if the source is not moving, the observer is moving toward the source. Then the opposite is true. Okay, so at the same time, when the observer moves away from the source, if the observer moves away from the source, that is the same situation here, then the VO will be negative. I think I've explained this one already, which is the same as that one. I think those are the basic idea which you have to know under this. Okay, so now from this question we can clearly see that the observer and the source, they are moving toward each other, meaning that on top there we have to use VO will be positive, okay, and VS will be negative. That is very, very important. Meaning that in this case, the formula which we're going to use is, I'm going to use the positive on top. So I'll use this formula now. I'll say VO will be equal to VS, open brackets, V plus VO divided by V minus VS, like that. That is the formula I'm going to use. So I can plug in the values now that I know my values. I'm trying to find this. So now we have been given the frequency of the source, because it's the one which was being emitted, which is 5.0 times 10 to the power 2 hertz. So I want to find this the frequency of the observer. So frequency of the observer will be equal to, the frequency of the source is 5.00 times 10 to the power 2, open brackets. This V is always constant. We are talking about the velocity, the speed of sound in air at 20 degrees Celsius. That is 343. So you always use 343 meters per second. So 343 plus VO, that is the velocity of the observer, which is 36.11. Then again here 343 minus the velocity of the source from our calculations is 0.5, like that. So we'll say VO will be equal to that is 5.00 times 10 to the power 2. That is 500. So I'll put a 500 here, open brackets. Then these two are supposed to be added. It will be 343 plus 36.11. I'm getting 317. Okay, yeah, I'm getting what am I getting now? So I'm getting 379.11. Okay, I've added. Now I'm not supposed to put plus. Then I divide 343 minus 25. that is 318, like that. So I'll get rid of this. So I'll get rid of this, and then I'll say the VO will be equal to, I'm going to say a 500 times 379.11. That is 180. Am I getting the correct one? So we are saying 500 times 379.11. Okay, so in fact, what we can do here, I'm getting a very big, I think it can just waste our time. What I can do here, I can just divide this inside here. The answer I'm going to get, I do times 500. So I'll say 379.11 divided by 318. I'm getting 0.1022411. This times the 500. So what am I getting? Okay, let's put it here. So we are saying we have 379 or 379. My calculator is having some issues. Let me use a different one. 379.11 divided by 318. Okay. Then I'm getting 1. Yeah, so now my calculator is now okay. 1.192. This times 500. Okay. So I'm getting the frequency to be 490 or 596.08 hertz. Now that this frequency which we are given is in 2 decimal places, I'll leave this answer to be just the way it is, in 2 decimal places. So that is the answer for this question. Okay. Okay, so now we're on question 4. So question 4 is saying, it's the same question under Doppler effect. A turning fork vibrating at 512 hertz falls from rest and accelerate at 9.8 meters per second. How far below the point of release is the turning fork when the wave of frequency of 485 hertz reach the releasing point? So now let's see. We have the observer and the source at the same time here. So a turning fork vibrating, the one vibrating is the one which was the source. Vibrating meaning it was emitting sound. Okay, so the source in this case is going to be this one, the one for 512. That is the source. So I have question 5, which is saying, okay, this question is under interference. So 2 loudspeakers are placed above and below each other as shown in the figure below, and driven by the same source at a frequency of 4.5 times 10 to the power 2 hertz. An observer is in front of the speaker to the light at a point 0 or at point O, at the same distance from each speaker. What minimum vertical distance upward should the top speaker be moved to create destructive interference at point O? Now this topic is very important and very interesting actually when we talk about the interference. So we have what we call the destructive interference and constructive interference. Okay. Now, for a destructive interference to occur, I think if you manage to watch my video, which I just posted recently under interference, I believe you managed to understand on how these interference they come about. So for a destructive interference to occur, the distance must differ by the original length must differ by plus or minus half a wavelength. Then for a constructive interference to occur, the original length must differ by plus or minus the wavelength. What does it mean? This is question 6. So this question is under standing wave. So let me read the question for you. A stretch string fixed at each end has a mass of 40 grams and a length of 8 meters. The tension in the string is 49 Newton. Determine the position of the node, antinode, for the third harmonic. Determine the position of the nodes and antinode for the third harmonic. But B, what is the vibration frequency for this harmonic? Now, the moment when you read the question, if they're not mentioning anything about harmonic, then just know that you are talking about the first harmonic. But in this case, they have specified to say we are talking about the third harmonic. So if we are talking about the third harmonic, then the number of loops is equal to 3. So we're on question 7. Now this question is coming from the standing wave in air column. Okay, so a pipe open at both ends has a fundamental frequency of 3.00 times 10 to the power 2 hertz when the temperature is at 0 degrees Celsius. If the temperature is at 0 degrees Celsius, using this formula to find the temperature, 331 meters per second times the square root of the temperature divided by 273 degrees Celsius. So if the temperature is 0, so we are now on question 8, the last question. So this question is a bit similar to the question we are from solving, which is question 7, but only that this one it is open at one end. So two pipes of equal length are each open at one end. Each has got a fundamental frequency of 480 hertz at 300 Kelvin. In one pipe, the air temperature is increased to 305 Kelvin. If the two pipes are sounded together, what bit frequency results?